Okay, so we are live on YouTube, and I think that we can start if you're ready.
Okay, thank you.
So welcome everybody. Sorry, Yane.
Go ahead.
Welcome everybody to this last theoretical lecture on Flavour and effective theory. Tomorrow we will have the tutoring class given by Olsir. And today we will finish with the last part of Flavour. And we have still Yerney that is giving us this lecture. So go ahead, Yerney.
Okay, thank you. So let me share the screen. Okay, so to recap, yesterday we kind of finished our discussion of with the message that a vast majority of flavor measurements, especially those related to the measurements of CKM matrix elements, show or validate a consistent description of flavor in terms of the standard model CKM mechanism. And this includes the description of CP violating phenomena in flavor physics. Now, today we'll actually, the goal of today's lecture is twofold. One is to try to better understand how we can actually derive predictions for many of these observables within the standard model, and also how we can then use this consistency of measurements with standard model predictions to put constraints or to probe potentially very high scales of new physics, or if you want to, or framed in terms of masses of potential new degrees of freedom, very heavy new degrees of freedom. So the overall theme will be flavor and new physics, but there will be a lot on theoretical techniques to actually access this physics. So let's start again with the, sorry, just let me move this a bit so it's not blocking my view. Okay. With the following simple discussion. So the question is that we want to answer hopefully by the end of this lecture: how much can new physics still contribute to flavor observables, given the overall good consistency of the CKM description? And let me give you a simple example. Another way of testing one of the unitarity tests of the CKM is related to the first row of the CKM. So we can perform the we can phrase the CKM unitarity constraint on the first row, and in particular the moduli of these matrix elements as extracted from various sources can be used to probe this unitarity condition. And in particular, in this case, for example, the modulus of the VUD matrix element can be extracted from super allowed nuclear beta decays. The VUS modulus can be extracted from semitotic kaon decays, and the VUB matrix element, CK matrix element modulus can be extracted from charmless semitotic B decays. So putting all these measurements together, one sees that the unitarity of the first row of the CKM is respected down to, let's say, a per mil, almost a per mil level, even though, as you see, that there seems to be a slight, perhaps a slight tension with CK unitarity in this particular instance, which actually has been gathering some interest in the community in the past years. However, now one can, using this information that we have, seek measurements which are dominated by leading order weak contributions, so tree-level exchanges of charge W's. And one can use these so-called leading order weak processes to extract the parameters of the CKM, and then using such reconstructed CKM, one can then use these elements to actually predict all the other flavor observables within the standard model. And with this, then one can actually compare predictions of all the other observables to measurements and consequently extract bounds on possible additional contributions in terms of some yet unknown new physics. In particular, what is conventionally done is that one uses these tree-level determinations of VUD, VUS, VCB, VUB, as well as the angle gamma from B to charge B to decay decays, as we discussed yesterday. And this allows to predict then standard model contributions, for example, to loop suppressed observables like neutral meson oscillation observables. So let's see an example of such an exercise. And before delving into the actual technical details of how one computes contributions of both standard model and new physics to flavor observables, let's start by just parametrizing possible deviations of observables of new physics of observables in presence of potential new physics. And in particular, let's go back to our description of neutral B-meson mixing and parameterize the contribution of the dispersive amplitude M12, describing the virtual contributions to BB bar mixing amplitude, and consider now this amplitude in the standard model, but multiplied by a factor which parameterizes potential new contributions relative to the standard model. And so these contributions can either modify the modulus of the amplitude of the standard model amplitude, or it can also modify the phase. So we have two parameters, which are here denoted with RD and theta D. And doing that, one can now actually rederive predictions for all the observables which are related to BB bar oscillations, like the oscillation frequency or the mass difference between the neutral B-meson eigenstates relative to the standard model predictions. And as we see, for example, the mass difference is only sensitive to the change in the modulus of the dispersive amplitude, while, for example, the measurement of the time-dependent CP symmetry as psi k short is sensitive only to the phase in this particular parameterization. And then one can also derive all the other observables and see how they are modified in presence of such general new physics. For example, also the semi-leptonic CP symmetries in B decays. And one can then superimpose all of these different measurements using standard model predictions with the CKM elements extracted from tree-level observables to actually put bounds on these new physics amplitude contributions, namely delta D. So in the plot on the right-hand side, which is unfortunately already almost a decade old, I couldn't find easily an update of this, a more recent update. But the main gist of it is that so here here we are looking at all the different constraints which are sensitive to this kind of new physics in the plane of the real and imaginary part of this new physics amplitude. And we see that the case of B sub D mixing, the new physics is allowed only to populate a region of parameters which is close to the standard model point. So very broadly speaking, up to order 20% corrections relative to the standard model predictions are still allowed by data. The situation is similar in the case of B sub S mixing contributions. And here, because the phase of B sub S, so the phase of relevant for B sub S mixing is not yet measured to such high precision, the allowed space or the allowed range of possible physics contributions here is somewhat larger. So this is how much we can say about possible new physics effects without actually referring to explicit new physics models or even yes, so putting it very generally. Now, if we want to go further, we need to understand the theoretical techniques that can be used to actually infer on effects of some heavy degrees of freedom on observables or measurements which are performed at much lower energies. And to do that, let me now switch to my tablet. So the content of this now will be actually a very brief introduction to the techniques of effective field theories. Now, effective field theory actually would deserve a completely independent set of lectures to really do it justice. So unfortunately, due to the limited time available, I will just try to give you a general understanding of these techniques. And for a more detailed treatment, I will try to forward a couple of references to excellent lecture notes, which are dedicated to the techniques of effective field theories. Now, the issue that we want to address, as I already said, is that in some calculations which are relevant for predicting measurements in low energy experiments, is that those calculations can involve very disparate scales. And the techniques of EFT then allow us to systematically take into account dynamics at a particular scale, ignoring the rest. Okay, so it allows us to break down a very complicated problem, which is computing a process which gets relevant contributions from many different scales, into computing contributions at one particular scale, and then moving forward. Okay, I think the tablet has lost connection again. Yes. So let me try to fix it. Okay. Yeah, so in the techniques then actually allows us to solve several problems which arise when doing naive perturbation theory, when we have actually a presence of several scales. And perhaps the simplest way to understand these problems is to consider not a flavor observables per se. I will discuss this even in the context of a simpler observable, and let's just consider low energy annihilation of E plus E minus into mu plus mu minus. Okay, so this is, as you know, this is a pure QED process, and it's at leading order in perturbation theory. This is mediated by a single photon exchange. Now, we can now ask the question, what are the weak corrections to this process? Okay, so what I mean by weak corrections, so we could imagine that at higher order in the weak couplings, electroweak couplings, we have effects contributing where, in addition to a photon exchange, we can also have a massive Z boson exchange, for example. Okay. Okay, plus others. Now, if you actually do an explicit computation of such contributions to the scattering amplitude of this process, you get a result which you can phrase in the following. So the scattering amplitude will, of course, the kinematics of the scattering amplitude, so the chiral structure and so forth, will be the one of the leading, so the Born amplitude, the leading order. So the first diagram would just give you 1. And then there are corrections. And if you actually compute from this particular diagram, the correction will be of the following form. There will be a numerical coefficient. And then, since this is a higher order in the weak couplings, it will be proportional to alpha over pi divided by the sine of the weak angle, potentially. And then there is a log, which is the log of the mass of the Z boson, which is exchanged in the loop, over the S, or put it differently, over the energy of the scattering squared, central mass energy squared. Okay, and plus there are other corrections. Okay, because there are many other diagrams and so forth. Okay, but for the moment, let's just consider this particular correction. The problematic thing about this correction is that it exhibits a sensitivity to UV. In this particular case, it does not seem to be overly concerning because the coupling constant alpha is small and the sensitivity is only logarithmic. And since the Z boson mass is while it's much heavier than the electron, the muon mass, the smallness of alpha still compensates, so the whole thing appears to be perturbative and does not pose a serious problem with perturbation theory. But consider this form of corrections more generally, and since we know that since we can, in addition to the weak bosons, now consider that we would have additional new charged particles at very high scales. We have no idea that they are there because we have no experiment which can actually produce them. But if they are charged, if they're charged electromagnetically, they could potentially enter such calculations. And since they can have of arbitrary large mass, they could potentially spoil perturbation theory. Or put it even more bluntly, so instead of thinking about now quantum electrodynamics and heavy particle corrections to low energy electrodynamic processes or observables, one can think of just gravity. Okay, so the problem that is present here, if phrased in terms of computations in gravity, is that computing, for example, which is much more severe, would be if you were trying to compute precise orbits of planets, you shouldn't require a detailed knowledge of quantum gravity. Okay, but if you do naive perturbation theory the way we did it now, this is not clear that quantum gravity could not spoil your classical long-range gravity calculations. Okay. What is worse is that you might say, oh, but this maybe happens only once at one loop, and then the other corrections will then still be convergent. But this is not true, because one can actually show that one can always, at any loop order, one can find corrections which will be of order. So at n loops, one can always find corrections which will be of order alpha over pi log mz squared over s to the nth power. And those kind of corrections are sometimes also called the leading logs. And the problem of appearance of these large leading logs, of course, is a pure perturbation theory artifact. Okay, so what we're dealing here is the fact that if we knew how to calculate this to all orders, of course, we would get the correct result. But we don't have these techniques typically. We need to rely on perturbation theory. And then these large logs, so this apparent sensitivity to UV physics in computing low energy processes, is due to perturbation theory artifacts. And the effective field theory techniques, when combined with so-called renormalization group improvements, they allow to so-called resum these leading logs and solve these perturbation theory artifacts. Okay, so before diving into the effective field theory techniques more formally or technically, let's try to gain some intuitive understanding of it. And so consider now particles, effects of particles with masses m, which are much bigger than the available energies in your experiment. Okay. Now, since they're much heavier, you cannot produce them explicitly on mass shell in your experiments. So the only way they can affect any of the measurement is through their virtual exchanges, so through quantum corrections. Now, a virtual exchange of a massive particle will induce non-local effects, so non-local interactions. And the non-locality will be of the order of the Compton wavelength of the exchanged particles, so lambda, which is of the order of 1 over m. Now, if you're doing experiments and performing measurements which probe distances L, which are much bigger than inverse, than this Compton wavelength, so at distances L, much bigger than 1 over m, one can then expand in a dimensionless parameter 1 over ml. Okay, and this expansion will be convergent. And in this expansion, each term in this expansion would now represent a local interaction. So what we've done is we've actually taken a non-local interaction and expanded it in an infinite series of local interactions. Later we'll see this is actually formally called operator product expansion, but let's continue with our intuitive understanding for the moment. Now, consider now the effects of this expansion on dimensional grounds. So let's perform first a naive dimensional analysis of what can happen in such an expansion. So the effects of the heavy mass in scattering amplitudes can come in form of two effects. One is logarithmic effects. So the heavy mass can come in logarithms of m over e, where e is the typical energy of the scattering that one is measuring, or it can come in powers of e over m. Now, it turns out, as we will show, heuristically at least, that the first kind of effects appear actually as normalization of parameters of the low energy theory, while the second form of effects appear as signal the appearance of derivatives acting on local operators, and this leads to what we call higher dimensional operators. So yes. And so to introduce this notion of renormalization and higher dimensional operators, let's introduce the so-called effective Lagrangian. Which now contains only light particles as degrees of freedom. And we'll start with a narrow notion of an effective Lagrangian, which we'll call L light, which will be the most general renormalizable Lagrangian with the emphasis on renormalizable, so up to dimension 4, consistent with Lorentz and gauge symmetries, which are respected by the low energy theory. Okay? And now the statement is the following, that such a Lagrangian can reproduce any scattering amplitude among light particles up to corrections which are of the order of E over M. Up to order E over M. So this is actually a complete description of nature up to corrections of the order E over M. Now, of course, this is usually not enough because these corrections can be extremely relevant, especially since these E over M suppressed corrections can actually break so-called accidental global symmetries, which are present in the normalizable Lagrangian because simply of its rigid structure, because it has a finite number of terms with a finite particle content. So it can have some accidental global symmetries present. And these E over M corrections do not necessarily respect these global symmetries. They have to respect the gauge symmetries, but not the global symmetries. Okay, so can break accidental global symmetries of L light. Now, a well-known example in the standard model are the baryon and lepton numbers, which are accidental symmetries of the standard model, and they can be broken if one considers the standard model as an effective theory, as we will do a bit later. But as another example, which is perhaps less intuitive at first, but more relevant for us at the moment, is that if we consider the relevant effective theory of quarks and leptons at the scale of 1 GeV, okay? So what is this theory? Well, this theory is basically just QED plus QCD, okay, at energies of the order of 1 GeV. So what are the relevant degrees of freedom? So we have the photons and the gluons, and then we have the first two generations of quarks and leptons, okay? So if we consider this theory and neglect, and write out only the renormalizable Lagrangian for this theory with this gauge symmetry, we see that it has a large Flavour symmetry. It has, in fact, a U2 connected to the up quark Flavour rotations times U2 corrected to the down quark Flavour rotations between D and S. So the first one is between U and charm. The second one is between D and S. And then we have the third one Flavour rotations between E and mu. And of course, there is a U3 connected to the neutrinos, okay? And this theory and this large Flavour symmetry is only broken at orders E over MW. By dimension 6 operators, namely the Fermi theory. So in fact, to be fair, there is a breaking of this U2 to the diagonal U1 squared by the masses of the quarks, but these are typically, especially in the down sector and the leptonic sector, these are small. Okay, because the masses are much smaller than 1 GeV. So one would have U1 to the 6th as the Flavour symmetry, right? And the symmetry is then broken by effects which are suppressed by E over M, as we said. Okay. Now, to formalize this discussion a bit, let's start with a formal justification that indeed the only effects of heavy physics on the low energy dynamics is in the form of these logarithmic corrections to parameters and E over M suppressed effects. Okay, and to do this, we consider the so-called Appelquist-Carlsson decoupling theorem. This is the content of this theorem. Okay, and we'll consider it in a very simplified case where we write the full Lagrangian of a model will contain the Lagrangian of light degrees of freedom, which are coupled to one heavy scalar. Okay, so we have a heavy scalar phi, which has the kinetic term, it has a heavy mass m, and it couples to light degrees of freedom. So we don't even care about the precise form of this coupling. Okay, what is important is that the only parameters of the Lagrangian element for the light degrees of freedom is in dimensionless couplings and masses. Okay, and then there might be additional couplings which relate, so which mediate the interactions between phi and light degrees of freedom. Now, the content of the Appelquist-Carlsson decoupling theorem is that if one considers Green's functions with momenta pi of light degrees of freedom, so Green's functions of light degrees of freedom, with their momenta being much smaller than m, then for any Green's functions for n particles, p1 to pn, in the full theory will be the same as a renormalized, so there's a renormalization factor z to the n half times a Green function computed in the only using the Lagrangian of the light degrees of freedom, p1 to pn, up to order 1 over m corrections. Now, this Green function is in fact computed using what we call the effective Lagrangian, which is the Lagrangian of the light degrees of freedom, however, with a twist, that's why we put a wiggle on top, is that this is a renormalized Lagrangian. Namely, it does not depend on Gi and Mj, but it depends on renormalized couplings, GI tilde, which are functions of the GIs in the full theory and can depend on the heavy scalar mass. And similarly, the renormalization constants which appear are also functions in general of the GIs and N. So what is important, why this is a non-trivial result, is that these renormalization conditions are universal. So they are the same for any green function. Okay. So there are two important results of this theorem is that there are no positive powers of M appearing in this expression. No positive powers of M. And furthermore, that any logarithmic dependencies on M can be absorbed into G tilde and Z and are universal. Okay. So yes. Okay. So now consider this. Now consider what happens. So as I said, we will be predominantly actually interested in effects which enter at 1 over M. And so let's see what happens. So this ensures, so while the Appel-Quisquaradzone ensures us that any effects of heavy physics can be absorbed into the redefinition or renormalization of the normalizable, of the parameters which enter the renormalizable Lagrangian, plus 1 over M corrections, we are actually now interested in these 1 over M corrections. So let's see what happens once we go beyond just considering the renormalized light Lagrangian, okay? So beyond light renormalized. So this will be up. So now we'll be concerned with contributions coming from to the Lagrangian density in the form of operators of dimension bigger than 4. And the formal way to compute this contribution is by using the so-called operator product expansion. Or colloquially, we say that we are integrating out heavy fields or heavy degrees of freedom. And let's show this again on a simple example, how this is formally done. And then we'll continue with a very practical way of doing it later. By considering the generating functional for green functions involving W fields. So in the standard model. So let's again consider we are thinking about low energy processes among quarks and leptons. And we're trying to figure out how the heavy W bosons affect these processes, okay? So let's consider the generating functional involving the W's, okay? So up to normalization, this will be given formally by path integral over the W plus W field, W minus fields times e to the I action, which is just, because it's a local action, just a phase space integral over the Lagrangian density involving the W fields, where we can now write this Lagrange density. And I'm working now in the electroweak broken vacuum. And for simplicity, let us choose the unitary gauge for the moment for this discussion. And so this Lagrangian involving the W fields will have of the form, we have the kinetic term plus times the same thing for the minus. Then we have the mass term for the w's, and then we can couple, since it's a generative functional, we're interested in currents coupling to w's, so let's write them explicitly. So there is a current plus coupling to w plus, and there is a current J minus coupling to W minus. Okay. Now, one can introduce in the unitary gauge, one can introduce the following kernel function, k mu nu of x, y, which would be delta, four-dimensional delta function, x minus y, times g mu nu, partial derivative squared plus mw squared minus delta mu delta nu, in terms of which up to total derivatives, one can rewrite the generating functional in a form which will be more convenient for our calculation, which is, so we have a path integral over w plus w minus times e to the I. And then we have, now we rewrite the first two terms in the original action as a integral over d4x, d4y, w mu plus of x, k mu nu, w nu minus of y. Okay. You can check by performing explicitly an integration over y, for example, or the difference between x and y, that one recovers the original first two terms in the action, plus while the coupling to the currents is of course unchanged. d4x, j mu plus w mu plus j mu minus w minus mu. Okay. Now, in this form, however, now we can perform the integration over the w fields explicitly. So we can perform this path integral now explicitly, written in this form, and we obtain the following generating functional form: e to the minus I g squared over 8 g mu minus of x. Now, where we've introduced the so-called propagator, delta mu nu x y, g nu plus of y, d4x, d4y, where the so-called propagator is, of course, the usual unitary gauge propagator for a massive vector field, d4k over 2 pi over 4, e to the minus I k x minus y over k squared minus mw squared times g mu nu minus k mu k nu over mw squared. Okay, now what we can do now, having the generating functional in this form, we can now actually perform a expansion in 1 over mw. Okay, so expanding in 1 over mw, we obtain for the propagator being g mu nu over mw squared times the four-dimensional delta function x minus y, plus high order terms in this expansion. What this leads to is that our generating functional now can also be expanded, and at leading order in this 1 over mw expansion, it will have the form g squared over 8 mw squared d for x j mu plus of x j minus mu of x. So what we've now done explicitly is to show that even though we started with a non-local interaction, which is mediated by the exchange of a virtual w, we have expanded it, and now we've written the whole generating function in terms of a series of local operators. And this is the first local operator in the series is a dimension 6 operator. So leads to dimension 6 operators. Okay. So now we can generalize this example, and in general, we see that we can write the full Lagrangian with this procedure of integrating out heavy fields. So at low energies, this will be, we can write the full Lagrangian as an effective Lagrangian, which will be composed of the renormalized light Lagrangian containing only, so it's the renormalized, so dimension 4 or smaller operator Lagrangian involving light degrees of freedom, plus an infinite series of operators of dimension bigger than 4. So this is operators of dimension smaller or equal than 4, of dimensions bigger than 4, which are, and these come suppressed by powers of d minus 4 of the heavy mass times the coefficient. So in our specific case, the coefficient was just g squared over 8 mw squared, which, like if written in terms of the Fermi constant, is nothing else but g Fermi over square root of 2. Okay, but in general, this will be some coefficients, ci d, which are often also called so-called Wilson coefficients. So these are Wilson coefficients times local operators of increasing canonical dimension d. Okay, and this is the gist of the effective theory. Okay. Now, where it becomes, so in this way, we at least now understand formally at least how we can account for heavy degrees of freedom affecting low energy processes. However, what we still haven't touched upon is how this allows us to account for these perturbation theory artifacts, this appearance of these large logs. So as we see now in this procedure, these large logs only appear in the normalization of the parameters of the light Lagrangian, and potentially in the normalization of these Wilson coefficients. Okay, so let's see how this helps us now to actually resound these leading logs. Okay, so what are the techniques to resounding these leading logs? So this is going to be these leading logs, as we will see, they appear once one goes beyond the leading order in the expansion, but not in the expansion of the heavy fields, but in the expansion of the light fields, or the light of the perturbation of light couplings. So if we go back and look at our example that we had before here of E plus, E minus to mu plus, mu minus. So we thought of this expansion as expansion around the Born amplitude for E plus, E minus to mu plus, mu minus by a single photon exchange. But however, in the effective field theory perspective, it's actually a different expansion. So the starting point of the second diagram would not be that there is a Z correction to the photon exchange, but there is a photon correction to the Z exchange. Okay, because at leading order in the interactions, this, after we first integrate out the Z, which leads to a local operator, and then we want to compute an electromagnetic correction to this local operator. Okay, and by reordering the, if you want, the reordering the way we do our calculation, this will allow us to actually resum these leading logs which appear. Okay. So let's see how this happens. So we are going now beyond leading order, but leading order in the parameters or couplings of the light degrees of freedom. Okay. Now, we will not do this formally, but we will now resort to very practical discussion of, in terms of Feynman diagrams. Okay, we'll not do path integrals, but we'll actually do Feynman diagrams. So diagrammatically, what we've just shown up here with integrating out the W, diagrammatically what happens is that since we're interested in the first non-trivial order, we can write this form a bit technically, although, that in the limit when the heavy mass, in our case this was the W mass, goes to infinity, the difference of m squared multiplied amplitude of the full theory, where with the W exchange, minus the amplitude given by a local operator. So this is just a local operator O, which in our case was just J mu plus J minus mu. Okay, that this difference when we send m to infinity goes to 0. Okay, this is basically the content of our previous path integral discussion, phrased in terms of diagrams. Okay. Now, let's see what happens to this identity when we consider higher order effects in the couplings in the light theory. For example, electromagnetic coupling, or what will be more important phenomenologically is the strong coupling when we deal with processes with quarks, like in Flavour transitions among quarks. Okay, so again, let's consider in the full theory, diagrammatically what we are doing when we consider high order effects is we are adding, so this is the leading order, and then we are adding corrections of, and just so I will not have to write the W and photon all the time to distinguish between wiggly lines. Let me consider processes involving quarks where I can have gluon exchange, okay? So just that visually, you always know which one is the heavy quantum exchange, which will be always the W or the Z with the wiggly line, and then the curly line is the gluon, so the gauge field of the light degrees of freedom, which is present in the light in the low energy theory. Okay, and there are many such diagrams one can consider. In particular, the one which is topologically similar to what we had previously in our example would be this one, right? Now, let's consider just very roughly the divergent structure of this diagram. So let's see how this diagram, the integral over the momenta present in this diagram scales, okay? So there's two fermionic light propagators which scale as 1 over k slash, okay? And there are two, so it's 1 over k slash squared. And then we have a gluon propagator, so it will have the structure of g mu nu over k squared. And then we have the W propagator, okay, which is again g mu nu minus the other term in any given gauge, k squared minus mw squared, okay? So in the limit of high k, this is a convergent loop diagram, okay? So there are no divergences. Now consider the same correction in the effective theory, okay? In this theory, at leading order, we just have the single insertion of the local operator. And then we can compute corrections to this by the exchange of light degrees of freedom, so in particularly photons or gluons. And now again, let's consider the corresponding diagram, which appears to have some visual correspondence. We'll see that the correspondence is not direct. What is the divergence structure in this case? Well, this case, the integral over internal momenta is of the form, so we still have two fermion lines in the loop, so still 1 over k squared. We still have the gluon line, g mu nu over k squared. But now, since we have a local operator, this local operator only gives us g mu nu over minus m squared, or mw squared. Now, this integral is no longer convergent, but is log divergent. So it cannot be that these two diagrams in the full and the effective theory are directly related. We cannot compare them. We cannot write such a limit as we've written out for the tree level diagrams. Okay. So what's happening? Okay. So the good thing that we will show is that the divergence, which is present in the effective theory side, is actually, in a sense, trivial, because it turns out to be independent of the momenta of the particles involved. Okay, and to show this, let's consider taking derivative of this amplitude with respect to the moment of the light particles. Okay, so let's write, so this is divergence is trivial, so independent of pi, okay, of the moment of the light particles. And now let's show that this is indeed true. So if we differentiate with respect to light momenta, so if we do it on the external legs, it doesn't change the divergence structure of the diagram. So nothing happens really. So where the difference comes in is when we differentiate one of the internal propagators, right? So in general, the internal propagator will be of the form k plus pi squared minus mj squared. Okay, so I've kept the mj dependence, which I didn't in the above. Okay, so before I just written 1 over k slash, but in case we have massive fermions, in practice this will be, when we differentiate, there can be also an effect of the mass. But what is important when we do such a differentiation of a light, and there might also be dependence, of course, on the loop momentum k, but we are not differentiating with respect to loop momentum, but with respect to external momentum. Okay, so we've kept the dependence on the external masses and external momenta, and then when we do that, we obtain, okay, just exactly, this is k plus p mu over k plus p squared minus mj squared. But what is important is that at high k, now this differentiated propagator will scale as 1 over k cubed. Okay, so even though we've differentiated with respect to the external momenta, we've increased the convergence of the loop integral, because now the fermionic propagators are more convergent once we differentiate with respect to external momenta. Okay, so instead of writing this limit that we had before, limit when m goes to infinity of m squared and the loop amplitude, we'll write the limit of one's differentiated loop amplitude. Okay, and in the full theory, this is the loop amplitude that we are interested in. Okay, and now, of course, we know how to do this. So at least formally, this will be m squared, and then the integral that will be present here is d for k, and there will be some dependence with, since now this is the each of the fermionic propagators, if we act on any of those, it will increase the convergence. So we can write the whole loop momentum integral as the k squared minus m squared piece times the rest. Okay, and now once we've differentiated, this rest is now actually convergent on its own. Okay, and we can do the same thing, the same limit in the effective theory now for this diagram. M squared, one's differentiated amplitude in the effective theory. And let's consider what happens. So also here now, since the only difference in the effective theory was in this propagator of the heavy field, since the rest is now convergent, it is also convergent in the effective theory. So both amplitudes are now, one's differentiated amplitudes are the same, okay, in the limit, okay? So this means that the non-differentiated amplitudes can only differ by a constant, which does not depend on the momenta, okay, of the light particles. So we can write out now this limit in the way that it holds. So m squared times this loop amplitude in the full theory minus the sum of loop amplitude in the effective theory plus a divergent constant times the tree amplitude in the effective theory, because the overall kinematic and chiral structure of the amplitude cannot change, okay? So the only thing, if we shift by divergent constant, is we basically just shift by a tree amplitude, okay? The important thing is that this constant is now divergent, but does not depend on momentum, okay? And this is 0, okay? So one can write this even more generally. What we actually have shown now, very heuristically though, is that at least to one loop order, m squared times the amplitude computed to one loop order in the full theory, plus all the other diagrams, okay, minus 1 plus c of the amplitude computed in the effective theory, including one loop corrections, are the same. Okay, so it's basically an extension of the Appel-Quist-Carazzone theorem, which said that the logarithmic, so the normalization of the dependence, logarithmic dependence on the heavy scales, which now is here signified by the divergences of the theory, is only contained in the normalization of the parameters of the normalizable Lagrangian. Here, what it says is that this normalization program also holds in 1/m local terms. Okay, so again, what this does effectively, it renormalizes the effective Wilson coefficients of the higher dimensional operators. So one can write this out now. What we've written out in terms of the in a diagrammatic way, we can also write in terms of Green's functions. So one can write out the Green's functions, in particular in our case, the 4-point Green function, which depends on P1 to P4, which is mediated by heavy W exchange, for example. In general, is mediated by a local, in the effective theory would be, so in the full theory, this Green's function is mediated by, technically it's the amplified Green's function. In the full theory, and it's renormalized, and it's mediated by the exchange of some heavy field, plus additional contributions from light fields, like higher loops of light fields, will be in the effective theory will be equal to in the effective theory to 1 over m squared times a coefficient. Basically, if I want to be consistent, this should be c, okay, as the Wilson coefficient, times a local Green function computed in the effective theory, P1 to P4, which is nothing else but the matrix element of the local operator, dimension 6 operator, where with a single, what is important is there is a single insertion of the operator plus, okay, so this is to the order 1 over m squared. In principle, they can be higher orders in 1 over m expansion. What is important is that this Wilson coefficient, which is here, is finite and can be expanded in the interactions or couplings of the light fields. So it's 1 plus C1 alpha over pi plus C2 alpha over pi squared plus so forth. Okay, where alpha is one of the gauge couplings of the light fields. So either electromagnetic or QCD in the standard model. And what is also important is that this Wilson coefficient is now finite and it's independent of the momenta and the masses of the light fields in a chosen suitable normalization scheme, of course, like the dimensional regularization with minimal subtraction. Okay. Now, so what is left is, so what we've seen now is that we've moved all of these logarithmic corrections of the logarithmic dependencies on the heavy masses, even at order 1 over m squared and higher, to this Wilson coefficient, okay? While the matrix element of the operator can be evaluated at any given scale, okay? In particular, at the low scale where the experiment is done. So how do we now, so we still have to, in principle, we still have to deal with large logarithms of the, so this C1, C2, and so forth. They are still functions of the ratio m over mu, where mu is the renormalization scale in our particular normalization scheme. Okay, so C1 of m over mu, and also of the couplings, okay, in principle. So, however, what we can use is, now we have this, so we basically, what we will do at the end, now it seems that we've taken actually a step backwards, because we've gone from having perturbation theory artifacts in the form of large logs to actually introducing another artifact, which is this arbitrary normalization scale, because we've chosen a normalization scheme which depends on choosing a normalization scale. However, this is actually a blessing, because what we can do now, we can use the fact that we know that the total amplitude, the complete result, has to be independent of the normalization scale. So what we can write out is we can write the condition that mu times d over d mu of the Green's function of the Green's function has to vanish, okay? And the Green's function in the effective theory is just the product of the matrix element of the local operator and the Wilson coefficient, okay? And so far we don't know actually how the matrix element of the operator depends on the normalization scale. However, we know that the complete Green's function has to be independent. So this means that if the mu dependence of the operator, so if the operator self-renormalizes in some way with some constant or some function, which is also called the anomalous dimension of the operator, okay, then we know that the Wilson coefficient has the dependence on the normalization scale of the Wilson coefficient has to exactly cancel that, okay? So it has to be minus the same function times c, okay? And now choosing a suitable renormalization scheme like the dimension organization with minimal subtraction, one can actually show that these anomalous dimensions will only depend on the couplings of the low energy theory, okay? Only on dimensionless couplings. And so what is remarkable in this procedure is now that the full dependence of these Wilson coefficients on M, on the heavy mass, are now completely fixed by the normalization scale dependence of the Wilson coefficients, because C can only be a function of M over mu, because these are the only two dimensional parameters. The rest are just dimensionless couplings in dimensional regularization with minimal subtraction, that is. So now we can use this insight to actually write everything in a closed form. So, but since I'm a bit running late, let me see if I can shorten this discussion. So what turns out at the end, so if we introduce the following, let's introduce t as the log of this ratio, and then one can derive that if the renormalized, one introduces renormalized couplings, so G bar I, which depend on t, so they depend on the scale t through t, and on the coupling G, where the coupling G is defined as being the renormalized coupling at the scale m, so at t equals 0, G, okay? Then one can write the following. One can show that C of T and G is now given at any scale mu, will be given by C of 0, so C at the Wilson coefficient at the scale m, and the renormalized couplings at minus t times a ratio of G prime at minus t over g prime at 0 to some power, let's call it d. Okay. Okay. Which is to leading order in the gauge coupling, light gauge coupling expansion is just a number. Okay. So what we've seen now is that what we've done is that we've actually, if we expand this in the t, in the logarithm, okay, one can see that this thing is nothing else but 1 plus g squared over 8 pi squared times a number times log m of mu, okay, to the dth power. Okay, so we see that this what this ratio of the renormalized gauge couplings at the heavy scale and at the light scale and any given light scale is basically resumming the leading logs of these amplitudes. Okay. So to summarize this procedure of integrating out heavy fields and constructing EFTs, it involves 2 steps. Okay, the first step is to compute the Wilson coefficient C at 0, which is called also the matching step. Okay, and this involves only calculations done at the heavy scale. So this is a calculation which is done at the scale m of heavy degrees of freedom. But then the second step involves running what we call running using normalization group equations, running these Wilson coefficients from the heavy scale down to the scale where we want to evaluate the matrix elements of the local operator to compute the actual amplitudes at energies which are relevant for our experiments. And this running step involves resumming these leading logs. Running is resumming the leading logs. Okay. Okay. So armed with this, at least I hope, an intuitive understanding of how EFTs can help us to perturbatively and systematically compute effects of heavy degrees of freedom on low energy observables, let me switch back to my slides. Okay. And discuss the following. Okay. So now that we know that we can actually think of any theory, if you want, so we can generalize our argument of effective field theories. We've seen that that given a full theory, we can, at low energies, we can approximate it with a renormalizable theory involving the light fields, plus a series of local operators. Now we can also invert the whole argument and say, okay, the standard model is a renormalizable theory of relevant degrees of freedom at scales below or around the TV. But we also know it's not a complete theory of nature because it does not involve a quantum description of gravity. It does not provide a unique description of neutrino masses. And also we have the problem of electroweak fine-tuning or the hierarchy problem, okay? So all of these issues suggest that there might exist additional heavy degrees of freedom, which we cannot probe directly in our present experiments. But now, armed with the EFT technology, we also know that the effects of these heavy degrees of freedom, if they exist, might be signaled by present or described effectively by the presence of an infinite series of higher dimensional local operators, which we need to add to the standard model renormalized Lagrangian. Okay, so this is also a picture of the same argument. Okay, so there might be some new degrees of freedom present somewhere at high scales where we don't know where. I'll come back to this picture later when we discuss the origin of Flavour problem. But consider now the standard model is effective field theory, so valid below some cutoff scale. So some, or in terms of our terminology that we used before, below some heavy particle threshold mass M, capital M. Okay. Now we can write now the effective theory where the standard model is just the Lagrangian limit of such a full theory, and now we can phrase the new physics Flavour puzzle in the following way. So for a natural theory, a theory which, like the Fermi theory, so we just integrate out some heavy particles with couplings which are order 1. We expect the Wilson coefficients, at least at the high scale, to be order 1. Okay. But then we are facing a problem. If there is new physics at the close to the TV scale, so these high dimensional operators are not too suppressed by the heavy mass, why? And we've performed many precision Flavour measurements, testing the CKM and also probing rare processes like B-meson oscillations. Why there doesn't seem to be effects of these heavy degrees of freedom in these measurements? So why we don't see large deviations in these precision observables? And so what we'll try to do, so in this sense, Flavour is often thought as a very powerful indirect probe of BSM physics, which sometimes goes way beyond the direct reach. And we'll try to use the next 10 minutes or so to try to understand why this is so. Okay, so pictorially, in terms of our discussion that we had now, so if we start with the standard model as our fundamental theory, okay, then we try to compute low energy observables like Flavour observables, which are done at the scales of order GV or below. We need to perform the same kind of EFT OP expansion. So we integrate out the heavy fields, the W, the Z, the Higgs, the top at the weak scale. And at the intermediate scales, we have the effective theory of weak interactions, like the Fermi theory, which can be systematically perturbatively improved, including high order QCD and QED effects, because we still have, of course, the QCD and QED degrees of freedom present. Now, once we go to very low scales, below the non-perturbative QCD scale, where QCD interactions become confined within, and QCD color degrees of freedom become confined within hadronic states, this effective theory of quarks and leptons and gluons and photons, again, is not the correct theory to describe the dynamics of hadrons. So we need to do another set of effective theory matching. In this case, what is nowadays often done when one computes processes involving hadrons is to perturb so-called non-perturbative matching. So one computes the matrix elements using not diagrammatic approach, but using, because at this point, the strong coupling becomes non-perturbative, so one cannot do perturbative calculations. And also the degrees of freedom don't match, so one cannot do perturbative calculations in many cases. In some cases, one can do, using quark-hadron duality, but in many cases, one cannot do perturbative calculation in terms of quarks and expect to get correct predictions for processes involving hadrons. And so what one does instead is one compute these matrix elements using numerical methods. Most importantly, the most precise way of doing this in the recent years has been using lattice QCD methods. Okay, so I haven't touched upon this additional step of matching effective theories of quarks and leptons down to hadrons and leptons. But just that you know, there's an additional step that is often required. And now what happens if we envision some heavy new degrees of freedom, which live at some high scale, so they have heavy masses way above the weak scale? Then again, we know that we can parameterize any such contributions in terms of a series of local operators. And such a theory, so the standard model of normalized Lagrangian plus this series of effective operators, is sometimes also called the standard model effective theory. Okay. And this standard model effective theory, in the standard model effective theory, all of these terms, all of these high dimensional operators have to respect the full standard model gauge theory. So namely SU2 left cross U1 hypercharged cross SU3 QCD of QCD. Okay. But it might not necessarily respect the accidental global symmetries of the standard model, like the baryon number and lepton number. And in fact, baryon and lepton numbers are broken at dimension 6 operator level in the standard model effective theory. Okay, so let's see one example of how we actually use these techniques to compute, for example, the standard model predictions for a neutral meson mixing observables. So, for example, how we compute the BB bar dispersive amplitude. So in the standard model, this is mediated by boxes and it's dominated by box diagrams involving top quarks and Ws. So after doing the matching step, one obtains a local operator, which is a 4 Fermi operator, and a Wilson coefficient, which at leading order is a function of the ratio of the top and the W mass, and it's here denoted by F, okay? And there is a prefactor, which is written in terms of the Fermi constant squared and M top squared to be of canonical dimension 6, because it's a dimension 6 operator. And it's because it's a loop order matching, there is also a 16 pi squared below. And then there is the typical CKM prefactor, which enters due to the 3 W vertices in the box. Okay. So what is interesting also is that one can actually rewrite this prefactor purely in terms of the Yukawas. So this is a way to see that actually, indeed, this goes back to our discussion in the first, the day before yesterday, that it's the standard model Yukawas which are the source of all flavor in the standard model. And any flavor observable can actually be written in terms of these parameters of the fundamental standard model Lagrangian. And in practice, one can, so this is now written at first order in QCD and QED interactions, but one can actually, using the techniques that I've introduced, one can actually compute this systematically improved to high orders in particular QCD, perturbative QCD interactions. And the final piece that one need, if one wants to compute this amplitude between mesonic states, not quarks, is to compute the matrix element of this local operator between the B and B bar mesonic states. And this last piece of the calculation actually needs to be done non-perturbatively, as I said, for example, using lattice QCD methods. And there is a way to parameterize these matrix elements, and the parameters are computed on using lattice QCD. Okay, so this allows us now to predict, for example, these relevant flavor observables in the standard model using these effective field theory techniques and non-perturbative calculations of hadronic matrix elements. And now we can imagine supplementing the standard model with additional operators which can contribute to these observables. And if we restrict our discussion to delta F equal 2, so neutral meson mixing observables in all sectors of down, K-on sector, charm sector, so D naught, and then B sub D and B sub S. So here I've written out 4 example dimension 6 operators which can contribute to these observables. And then one can use the measured values of the relevant observables in all the sectors to actually put constraints on these contributions. Now, so here I've denoted the suppression mass scale by lambda new physics and the Wilson coefficient with Z, okay, just to compare with the previous notation. And now what happens is that provided we assume that these Wilson coefficients at the high scale are order 1, then we see that the present measurements of both CP conserving and CP evaluating observables related to neutral meson mixing constrain these new physics to lie at very, very high scales. In particular, the most constraining, as I already advertised the day before yesterday, was the measurement of CP evaluation in kaon mixing, epsilon k, which probes scales as high as 10 to the 4 or parts of 10 to the 5 TeV. Okay. So what this tells us immediately is that new physics with a generic flavor structure, where these Wilson coefficients are order 1, is irrelevant for solving the electroweak hierarchy problem. So cannot live at the TeV scale, because flavor bounds tell us that such physics has to be really heavy to be consistent with flavor measurements. Okay, so it's also a picture of this a compendulum of constraints in terms of probing. So this is now more general because I've not included only these operators, but all possible chiral structures of operators. So you see that in fact, once one includes other chiral structures, some of those are much more constrained. And in particular, epsilon k probes scales up to several times 10 to the minus 5, in fact.
Yeah, mate. A couple of questions. What you just said is valid for generic new physics where that does not any flavor rule, in the sense that
exactly, yes.
Because so, if there is a flavor physics that does know something about flavor, it could be that this coefficient can be a little bit smaller and the scale can be
exactly. That's why I've written this in terms of square root of ZSD. So if ZSD, for example, which is relevant for kaon physics, is much smaller than 1, then of course this can compensate and you can have new physics at lower scales, of course.
And another question, do we still consider the beyond the standard model Lagrange to be renormalizable?
So here, as you see, these terms that are written out are manifestly non-renormalizable, right? They are dimension 6 operators. They are not renormalizable. They're not dimension 4 or smaller.
Yeah, the question is about the beyond the standard model Lagrangian to be normal.
Oh, the full one, the full. Well,
I guess that this is the question. Yes.
Yeah. So at energies below the mass scale, we don't care. That's the question. That's probably the answer, right? So once we are at energies below the mass scale of the heavy degrees of freedom, we don't care and we don't know. There's no way we can tell, because these degrees of freedom are never produced on shell, and all their effects are coming from virtual exchanges, and they are encoded themselves in non-renormalizable interactions among the light degrees of freedom. What we know is that we can encode any effects with this standard model effective theory in this case. Any kind of effect from any kind of heavy new physics consistent with local field theory can be encoded in the standard model effective theory if one consistently expands to all order in the heavy mass.
Okay, great.
Okay. So that's in a sense, it's a very powerful technique in principle because it allows to encode anything that happens at the high scale. Of course, the drawback is that the number of parameters, the number of these Wilson coefficients grows exponentially at higher powers. So the predictivity becomes worse and worse. Now, as we said, we can also turn the whole argument around and try to understand why these severe constraints on new physics. And we can trace this back to actually this particular hierarchical structure of standard model, because the predictions of these, so as we said, we can treat the standard model as an effective theory below. So once we've integrated out the top, the W, the Z, we have an effective Fermi theory of weak interactions. And then we can actually see what the standard model contributions to these operators are. And by doing this, so at energies of the order of a GeV or so, we can see that the Wilson coefficient and the standard model are much, much smaller than 1. They are not, so the scale now, the lambda of the standard model is the weak scale, but the Wilson coefficients of the standard model are not 1. So the standard model is not a generic theory because it has a very particular hierarchical flavor structure. And in fact, these Wilson coefficients in the standard model are very small. In the case of the imaginary CP-validating contributions to KL mixing, the relevant parameter is 10 to the minus 10, okay? And so we see now that in order for new physics to be at low scale so that it can be relevant for electric hierarchy problem, for example, the TV, then also this new physics has to mimic this hierarchical structure of flavor. And in particular for TV scale new physics, the Wilson coefficients, especially relevant for kaon mixing, have to be tiny, for example, of the order of 10 to the minus 6 or so. Okay. Or if it's CP validating, even smaller, 10 to the minus 7. Right, so one can, just to conclude, one can actually do the same, and also because this has been very interesting recently from the experimental and phenomenological point of view, until now I've phrased all the discussion in terms of neutral meso mixing experiment observables, but actually a very interesting case can be made in rare decays. So basically delta F equal 1 flavor change neutral current mediated observables. And as an example, let me now write another set of operators which can contribute to flavor observables. And these are called so-called Z penguin observables. So these are basically flavor changing couplings of quarks to the Z boson. Okay. Now these are also, of course, one can compute effective contributions to these. So the relevant observables here will be rare decays of mesons like kaons and B mesons. And similar to the case of neutral meson oscillations, also here the standard model effects are severely suppressed because they appear at loop order. So standard model, as we discussed the first lecture, does not have flavor change neutral currents at the tree level. But in addition to being loop suppressed, they are also CKM suppressed. So there is this, they're also suppressed by the hierarchical structure of the CKM. And so this leads to very small rates for these flavor change neutral current mediated rare decays. In particular, there are two sets of these measurements which have been updated recently and are very interesting to consider. First are the very rare kaon decays, K to pi mu nu bar. So kaon decays to pions and neutrinos. And these have been actually measured. The branching ratios are tiny, of the order of 10 to the minus 10. And they can be predicted precisely in the standard model. And the comparison to the recent updated measurements by NA62 experiment at CERN allow us to constrain such new physics, which couples flavor changing D to S currents to the Z boson up to hundreds of TeVs. Okay, so such new physics with generic flavor structure, of course, would have to be heavier than 100 TeV or so. So already severe constraints. A similar constraints can be put looking at rare leptonic neutral B decays, so B sub S and B sub D decays. These have been observed by the experiment at the LHC. In particular, the most precise measurement of B sub S to mu plus mu minus has been performed by LHCb, but there are also complementary measurements being done by CMS and Atlas. And the standard model predictions for these decays are very precise and are shown in the black, and they are reasonably consistent at a bit better than 2 sigma level with the current most precise measurements, which are shown. The world average is shown in the red, the full combination. Okay, and then concluding with the most intriguing measurements. So these same kind of effects, potential new physical effects, can also be probed with rare semi-leptonic B decays. And why are these interesting? Because in this case, even though the rates are actually more difficult to predict, the differential rates, compared to the fully leptonic case, one has many more observables that one can actually construct, because one has the kinematical information on the final state muons and kaons. So in fact, one can do a differential rate analysis using several angular observables, some of which can actually be predicted with somewhat better precision than the rate itself. And this is below is shown the full angular decomposition of this particular differential decay rate. And while there are challenging theory uncertainties, and there is an ongoing discussion of those, what is intriguing is that there in the past decade, there have been some intriguing persistent deviations in some of these observables appearing when compared to the most recent standard model predictions using techniques to try to address these hadronic uncertainties in these decays. And what is even more intriguing is that one can actually form very clean ratios, which are called so-called lepton-Flavour universality tests, where one, instead of trying to predict and measure the rates of these rare semitonic B decays, one forms ratio of rates of different lepton flavors. Now, what happens is that in this case, all of these very challenging hadronic uncertainties cancel to a very large degree. And so the predictions in the standard model for these lepton universality rates are typically very precise. In the case of B2K mu plus or minus over B2K E plus or minus, the expected corrections come at the per mil level, but definitely below the percent level. And intriguingly, LHCb has measured very precisely these ratios, and they seem not to agree. The measurements does not seem to agree very well with the expectations within the standard model. So this might actually be pointing out to some form of new physics. And if you're interested, what's the scale of new physics that will accommodate this? The scale is actually for generic flavor violation is in the order of tens of TeV. So unfortunately, it seems to could be above the present reach of direct colliders at the LHC, but nonetheless very intriguing. Yes, so let me finish at this point with this interesting recent results.
Yes, definitely. It's very interesting, and thanks a lot for this instructive lecture. Could you tell us a little bit what will be the topic that Olsi will treat in tomorrow?
Yes, so I don't know if Olsi is here, so then he could tell it himself. Let me see if
I don't see her actually.
Oh, okay. So he will take a couple of examples of the different results that I've shown from all the three lectures, like the Yarlskog invariant which is a measure of CP violation, in the first lecture. And so let me see exactly. And I think he will also do an example of he will do an example of this last topic that I did. So the of rare flavor-changing intercurrent mediated rare semitonic B decays, where there are these interesting apparent deviations of experiment from the expectations. And he will do some explicit examples of how one can estimate the effects of new physics in those observables.
Okay, great. In the meantime, there has been a question. I would like to ask, what is the connection to all these anomalies That is, if they point to the same direction regarding possible UV explanation.
So there are a number of attempts in the literature where people try to construct more or less effective or toy examples of UV models. We try to accommodate a subset as large as possible of a subset of the presently observed deviations. No, so the smaller the subset, the easier it is. No, so for example, if one just restricts to the rare so the rare B decays, in fact, the deviations, for example, in angular observables in B to K star mu plus or minus, and lepton flavor universality ratios in B to K mu plus or minus or B to K E plus or minus, they can be fairly easily accommodated using a very simple model. And it also can account for the slight tension in the rare leptonic B decays. There are also somewhat related, I mean, we don't know if they're related. There are also apparent deviations in lepton flavor universality ratios of charge current mediated B decays. There, when one compares semi-leptonic B decays to light leptons, so muons or electrons, and with respect to those decays involving taus. And there also seem to be deviations from the standard model predictions there. And one can try to build models where all of these lepton flavor universality deviations are accommodated. And also this is possible with, although the models are no longer very simple, if you want for them to be consistent field theories. But then if one wants to furthermore account for other recent anomalies, for example, the G minus 2 muon, then again, the models become, there is more and more model building that needs to be done to accommodate all of these anomalies. It's not really clear or apparent that all of these anomalies point to kind of the same very simple picture of new physics in the UV.
Okay. So if there are no other questions, I think we can stop here. Thanks really a lot, Yerney, for these beautiful lectures, and hope to see you personally soon.
Yes, very much.
So see you tomorrow morning for the tutoring class on flavor and effective theory, and after it there will be the visit, the virtual visit to CMS.